present our project for Dr. Habbash, and my name is Khalid Avdiya, and my partners are Abu Bakr Irfan and Anan Ahmed, and today we're going to present to you how to realize a PID controller. So this is important to take your plants that you create on, let's say, MATLAB in the S domain and create it into a real life circuit. So as you know, the PID is made of three different controllers. So the proportional, which is Kp, and then you have the integral, which is Ki over S, which has a zero value, and then you have the differential with the pole, which is Kds. And when you add all of them up, you get this following equation, Kds plus Kp plus Ki over S, which gives us the following format for the equation. And now we're going to show you how to realize this. So to realize PID controllers, one way of doing this is to realize each part of the controller alone and then summing it all with a summing amplifier. So for this slide, we're going to show you how to design a proportional controller using an inverting op-amp. So as you know, the gain formula for the non-inverting op-amp is given by R2, negative R2 divided by R1, where R2 and R1 are the resistance value of the op-amp. And you can tell that this is an inverting op-amp since the positive is grounded and the input is going to the negative terminal of the op-amp. So a quick example is to show you how to design a controller with a Kp of 30. So one way of doing it is to design the resistance values, and obviously it's open up. You can choose your own values. For this case, we know that the gain of negative 30, which will be inverted later on to a positive value, is given by the formula negative R2 divided by R1. So for our case, we decided to make R2 a value of 30 k ohms while keeping R1 as 1 k ohms. And as you see, when you insert these values into our gain formula, we do get a gain of negative 30, which is what we wanted. So for the second part, we're going to be designing the integral controller. And likewise, as a proportional one, we can use an inverting op-amp in order to design such controllers. So the gain formula for this op-amp with a resistance value and a capacitor value instead of two resistance values as the proportional controller is given by negative 1 over Rc divided by S. And like the last example, we wanted to show an example for an integral controller, which we decided to be 400 divided by S, and we're going to design the values in order to get these. So all we have to do is set these gain equations equal to each other, multiply this by negative, since we're going to be inverting it again back to positive values, so we get this equation, negative 400S equals negative 1 over Rc divided by S. And by using simple math, you reach to this stage where you have Rc divided by 1 over 400, which gives us a value of 0.0025. So at this point, we can design either a resistance value or a capacitor value in order to get this, this number. We decided to design our capacitor value, which we gave it a value of 10 microfarad. And when you do insert this, it means that our resistance value has to become equal to 2.5 kilo ohm. So for the last part of the PID controller, we're going to be designing the differential controller. And we're going to be using the same inverting op-amp, but this time we're going to have the capacitor value on this side while the resistance up there. And using this setup gives us this gain formula, negative Rc S. So we're going to use another example this time. It's going to be the differential controller, which is going to be 20S, and we're going to design the value. So we're going to multiply this by a negative sign. We're going to equal them together, which gives us this. Then we get this equation. And now we just need to choose either a C or R value that we can later adjust the other value to get 150. So we decided to choose our capacitor value as 100 microfarad, and then when we insert that in the formula, we get R to equal 200K. So if we do enter these these values into our op-amp, we do get this gain. And for the last part, we're gonna join all of these together into one circuit and demonstrate how it would look like. So for the last part, as mentioned, we do take all these controllers that we designed and we add them up, and we get the following circuit, which has the PID controller and the plant, and it's a motor for this example. So the PID values that we had from before are all added up with the equation that was mentioned at the beginning. So we have 30 for proportional, for the integral we have 400 over s, and for the differential we have 20s. And it gives us this equation. So now, this is how this circuit starts. So these are the parts of the PID controller. One was the proportional that we had these values for. R1 was 1K, while R2 was 30K. And these are the values right here. And then the second part was the integral, and these were the values that you enter for these, capacitor and resistance. And last but not least is the differential, which is this one, and these were the values that were calculated. And all these are added up into the summer. So it makes up the PID controller. And as mentioned, all of these had negative values, and it was mentioned that at the end it will be reverted back to positive. And the way it's done is through an inverting op amp, where it takes the negative values and it makes it positive. And then it's given for the plant. And the feedback is all given back to the beginning, to the op amp at the beginning. And that is how to realize a PID controller. Thank you.